A few bits of information about the midterm. So I posted a study guide for the midterm. There's a link to it on the Triton Ed page and also on the class web page. It's just basically just a list of topics. It's an overview of sort of the important things that you're supposed to know. I also posted some problems, an additional problem list on WebAssign, just basically to give you guys problems to practice on. Because I think you can't do problems on WebAssign unless I've given them as an assignment, right? Like if you wanted to just go do more homework problems, I don't think you can do that. Not that I know of. Anyways, yeah, so I posted some problems that'll give you more practice with things like substitution, which is obviously really important, and integrating by parts and all that. And I'm going to do a review. I will do some review on Monday to prep for the midterm as well. So I think that's all the midterm business I have. All right. Any questions on any stuff or things? Then we can pick up where we left off on Wednesday, which was talking about these polar graphs. I'm doing the material from 11.3 and 11.4 and kind of at the same time, simultaneously. And the last thing that I did on Wednesday it's a new area formula. In section 6.1, we learned about doing areas in the plane, but that was all rectangular coordinates. So now here's a new area formula for polar coordinates. And the formula was 1/2 the integral from alpha to beta of f of theta squared d theta. And what it gave you was if you have some curve r equals f of theta, and you want to find the area of a certain portion of it where this is at angle alpha and this is at angle beta, then what this formula gives you is this area right here. Not that. And the next thing that I was going to do with this formula was apply it to an example that I was showing you guys. Right, there's all these sort of crazy polar graphs you can get. In fact, it's pretty fun if you get out a polar graphing utility to just try plugging in weird formulas and see the different sorts of shapes you can get. So the one that I had left us off working on, the example that I was doing was r equals 1 plus cosine theta. Yeah. So this gal was a shape that looked like this, the cardioid, or acardioid. So when I was first talking about this shape, it was in the context of figuring out what a polar graph looks like. And we plotted some points. I made a table of values, if you recall, of r and theta in order to figure out what this looked like. Now we can find its area. So let's try practicing using our new formula and see what's this area right here. Probably the hardest thing to figure out in applying this formula is what alpha and beta are. That's going to be probably the challenge on some of the homework problems. It's sometimes you can't always tell by looking at it. In this case, I think it's okay. Like if I just plot some of the points, let's see, this was the point where where theta was 0 and r was 2, was right here. We had other points like right here, for example, theta was pi over 2 and r was 1. Right here we had theta was pi and r was 0. This point, theta was 3 pi over 2, r was 1 again. And then, in fact, I could have kind of traced out a path of this curve as we increase theta all the way up until the point is when I get back to here, this is also the same as theta equals 2 pi. So I can use 0 to 2 pi as my limits of integration. So I'll get 1/2, 0 to 2 pi. Oh, this, by the way, is my f of theta. So it'll be 1 plus cosine of theta squared. Anyone spot a symmetry here? Like if I really wanted to, I could cut this thing in half and just do the top half and just double it. That should give me the same answer. It doesn't really save me much time here, so I won't bother, but there are situations where that would save you time. I'll just leave it like this. So let's see if we can do this integral. Let's see, this is the integral of 1 plus 2 cos theta plus cos squared theta. Looks like I put in an extra set of parentheses that I don't need. So this is 1/2. Integral of 1, that's theta. All right. Cos theta, that's not too bad to integrate. Okay, so integral of 1 is theta. Integral of cos is, was it sine? And this term, I'm going to leave it. In fact, what's the problem with this term? These first two were easy to integrate. You guys know how to integrate cos squared, though? I don't know if I've showed you guys or if you should know. Who knows a way to integrate cosine squared? Sorry? We can use a trick. What's the trick? I don't know if you guys should have seen this trick or not yet, but I'll tell you right now it's really important, and expect to use it on the midterm, for example. So the trick is to use an identity, a trig identity on cosine squared. So whoever taught you your pre-calculus should have definitely taught you that cosine, let's see, what's the identity? Cosine squared of theta is 1 plus cos 2 theta divided by 2. And the reason that that's important, or that's useful here, is because this is easier to integrate, actually. So let me replace it. Let me replace cos squared with that identity. So it becomes the integral of 1 plus cos 2 theta over 2. In fact, here, let me put the 1/2 in front. So theta plus 2 sine theta plus 1/2. I'll put my limits of integration in at the end, by the way. So the integral of 1 is theta, and the integral of cos 2 theta is, hopefully you guys are good at this by now. I'm just going to do it in my head. That's sine 2 theta divided by 2, which, if you're not sure how I was able to get that, it's with a u substitution that I basically just did in my head. And let's put my limits of integration. They were 0 to 2 pi. So I'll get 1/2. Okay, that's a 2 pi. Sine of 0 and sine of 2 pi is 0. Plus 1/2 of, let's see, that's a 2 pi. Again, sine is 0 at 0 and 4 pi. Okay, it's 3/2 times 2. That's 1/2 times 3/2 times 2 pi. That's 3 pi over 2. Any questions on that? Okay, so yeah, definitely make sure that you could do something like this if you were asked to reproduce it on an exam, for example. Let's see, what did I want to do next? Okay, let's talk about some other polar graphs. Like I said, there's a whole bunch of cool, interesting ones. A lot of them look like flowers, actually. So let's look at, how about, okay, let's look at sine this time. What about sine theta? This one is a really boring flower. In fact, we've already done it. In fact, okay, it's not even really a flower. Anyone know what shape this is? It's just a circle. Yeah, we already did actually this. This is just a circle right here centered at 1/2. Okay, so I'm not going to do that one. But what I will do is try putting a number in front of theta right here. So I'm kind of like increasing the frequency. Let's do r equals sine 2 theta. Okay. Now, should I graph this using a table? Yeah, I guess I should just... Okay, let's make a little table real fast and see, see some points on this graph. Now, you'll notice that when I graph these using the table, which is something you should be able to do, it really helps if you remember your sine and cosine graphs. Like, if you're thinking about what to put on your cheat sheet, it should definitely have the graph of y equals sine x. I mean, unless you just have this memorized and can do it in your head, which is even better. But if you don't, then, you know, either use a unit circle or the graph, whatever you need to make sure that you can plug in points here. So I'm going to do 0. I'm going to do pi over 8. Pi over 4, 3 pi over 8, pi over 2. Let's see what this looks like up to this point. You'll notice I'm deliberately choosing angles that when I double them, I'll get angles that I can evaluate the sine of. So again, like it took a little bit of forethought to see what to choose which theta angles I wanted right here. I'm choosing all angles that once I double them give me something that's easy enough to evaluate with the sine. So sine of 0 is 0. Sine of pi over 4 is 1 over root 2, which is approximately 0.7. This is sine of pi over 2, which is 1. Sine of 3 pi over 4, that's also still 1 over root 2, which is about 0.7. Sine of pi is 0. Okay. So at 0, it's 0. Let me just draw this. This is theta equals pi over 4. At pi over 8, it's about 0.7. Let's say this is 1. So that would put me about here. And at pi over 4, it's 1. And at 3 pi over 8, it's 0.7 again. And then at pi over 2, it's 0. So if I trace this out, this is what it looks like. It's starting to look like a petal of a flower. Now, if I graph, this was a graph of sine x. Let's graph, how about sine of 2x, for example, which looks like this. If this is 2 pi, this is pi. Yeah. Now, I only went as far as pi over 2 so far in my table right here. So that was kind of this first bump here gave me my first lobe here. This second one is going to look like much the same thing, but because it's negative, the radius is going to be pointing in the opposite direction. So, I mean, I could keep on plugging in points on this table, but I'm just going to say I can see the pattern here. And on this stretch of the graph of sine x, it's going to be a lobe, but in the negative direction. And if you trace where this guy is going, it's going to do this. There. So maybe you can see this sort of trajectory. Basically, what I'm just getting is what I would get if I, for example, let's say I plug in, this is theta equals 3 pi over 4. If I plug in 3 pi over 4, I get sine of 3 pi over 2 is negative 1. So that would correspond to this point right here. Okay. Again, since I don't want to be here all day, I'm just going to say I can pretty much see where things are going, and I'll just fill in the rest of this now. So this lobe right here is going to correspond to this petal, and finally this one right here will give me this one. And that brings us back to where we started. So we got our 4-petaled flower. that was, I said I constructed that flower by, so that the first thing I did was r equals sine theta, was just this circle. Then I made it a 2 theta, which gave me this flower. What about a 3 theta? And I'm talking about this because you're going to have to work it out on your homework too. So moving up to r equals sine of 3 theta, I really don't feel like making another table. This one's going to be really annoying. I would have to do like angles like pi over 12. We're going to make a table for this guy. Let me just try and graph. How about do a graph of y equals sine 3x, and maybe we can guess from that. Okay. So let's see. Sine is 0 at pi, so x must be pi over 3. Okay, so this point, you guys in the back can see this. So this is pi over 3 right here. This will be 2 pi over 3. This point, let's see, I'm just going up in, well, that's pi. This will be 4 pi over 3, 5 pi over 3, and 2 pi. Okay, so just like in that example, each one of these corresponds to a lobe. Where's the peak of this first lobe? It's right here, which is at pi over 6. So I'm going to get a petal whose peak, let's try to draw this right. Okay. So this is when theta is equal to pi over 6. This one, this is a pain. What is this point? Pi over 3, 2 pi over 6, pi over 2? Yeah, this is at pi over 2. So I'm going to get a negative, like I'm going to get the farthest point of a negative lobe pointing up in the vertical direction, which corresponds to going backwards. And then this guy, let's see, what's this point right here? These are freaking annoying to calculate. Let's see, this is 5 pi over 6? Yeah, that's at 5 pi over 6. Okay. 5 pi over 6. That points now, if you tried to continue to graph these guys, like for example, this one right here, let's see, that's at 7 pi over 6. Actually, 7 pi over 6, which points in this direction. Can you guys see what will happen if I try and plot this lobe at 7 pi over 6? It overlaps with the one that I already drew, actually. Right? Because it's negative. So it's like pointing in this direction, but negative is actually just the same one as this one. So my point is I can stop graphing right now. I'm done. If I continue to plot points, it just overlaps this on the circle on the rose flower that I've already drawn. So this is the entire graph of this guy. Now, yeah, this graphing of polar equations is kind of a pain. You need to make sure you know how to do it, and then we'll never have to do it again, probably. Well, I mean, I don't know. Maybe you guys as engineers will have to do it, but I don't think we're going to do it very much again in this class. So how about, okay, let's get the area of one of these petals. So new question, let's find this blue area. So I have the area formula. It's alpha to beta of 1/2 f of theta squared d theta. And there's my f of theta. So I'll get a 1/2 sine 3 theta squared d theta. And like I said, sort of the kind of challenge here is finding the limits. Can you guys see what the limits are? If you mess them up, you'll get the wrong area. So the limits, here, look at what was the angle, what angle was this, and what angle was that? Those are my two limits. Yes, actually, yeah, right. This was theta equals 0, and this was, yeah, right when it hit 0 again, which was at pi over 3. Good. So we'll get 0 to pi over 3. How do we integrate this equation here? It's got a sine squared in it. So I did this deliberately for a reason, because once again we have to use a trick, but we've already seen the trick today in this lecture, more or less. What was it? Trig identity. I did it for cosine. Well, there's also a double angle, half angle. It's like a half angle formula. Whatever it's called, we can use the trig identity that sine squared x is 1 minus cos 2x over 2. So this thing will equal 1/2 the integral of 1 minus cos of 6 theta over 2 d theta. And yeah, and then you can. I'll let you guys finish that one. It's a lot like this problem here. So I can just stop this one right here. You guys can work it out if you want to see what the actual numeric number is. Okay, so that would give us the blue area of this petal right here. Okay, so when we were introduced to areas back in chapter 5, then the next thing we did in chapter 6 was we said, okay, so the integral is the area underneath the curve. Let's take the area between two curves. So that'll be the next thing I'm going to do here, except now it'll be the area between two polar curves. And it'll look a lot like what we've already seen. So this will be for the situation where we've got one function of theta and how about some other function of theta, and I want to find this region right here where, say, this is angle alpha and this is angle beta. So just like kind of what we did before is you take the outer area and subtract the inner one. Or, okay, when we did it in rectangular coordinates, we would take the function on top and subtract the function on the bottom in a dx integral. In a dy integral, we had to take the function on the right minus the function on the left. Here, it's not on top or bottom or right or left. It's the outer function minus the inner function. And you can kind of see in this picture, clearly, this is the outer function. And the g is the inner function. Remember I had to make that definition before we could subtract the top from the bottom? The region had to be simple enough in like a certain way. I said it was vertically simple when there was clearly one function on the top and one function on the bottom. I said it was horizontally simple when there was clearly one function on the right and one function on the left. So we'll have a similar terminology here. We'll call it radially simple when there's clearly just one outer function and one inner function. So let me make that a little bit more precise. This will take me a second. So we call a region radially simple if, let's say a region R, radially simple if every ray from the origin through R intersects R in at most one segment. So that's basically like, okay, if I draw a bunch of rays here, you can see the intersection is, in this picture, it's always just one segment. Or maybe no segment at all, like here it doesn't even intersect. But in the region, at least the part that we care about, if it intersects it, it's just one segment. Okay, so then that is the situation where I can now just sort of easily define what this blue area is. And it'll be like the outer area minus the inner area. So that'll be the integral from a to b of 1/2. So we'll take the outer function squared minus the inner function squared. It's basically, it's like I'm taking the outer area and then I'm subtracting off this inner one, and what does that leave is the blue one. And the idea, like you can kind of visualize it geometrically. So, okay, this is your formula in case you need to take the area between two polar curves. So, like for example, let's look back at this one, and okay, this is going to come up on a homework problem. What if I drew a circle. Let's see, where's about 1/2? Let's see, this is about, here's about 1. Here is about 1/2. So this is the circle r equals 1/2. And now, what if the new question was to find, forget the blue area, let's do the red area. Here, let me draw it. Okay, this is going to get very colorful. So let's find the red area. R equals sine 3 theta. Here's the problem, though. Okay, like, what would you say is the outer function and the inner one? What's the outer? To get that red area, what's the outer one? It looks like it's the circle. I mean, you're right, actually. It is, except there's a problem. That formula will not work if you try to treat the circle as the outer function here. And here's why. If you did, it would give you, now this is going to be kind of hard to draw. Maybe you can see it. It actually wouldn't give you the whole region. It would only give you this region, but you'd still be missing this little sliver right here and another sliver on the bottom. If you tried to integrate from this angle to this angle with the circle being the outer formula. So in fact, and you guys will have to do this on a homework problem, the way you have to do it is calculate the whole petal, which we already did, and then calculate the part outside the circle of radius 1/2, but inside the petal. And then if you subtract that from the whole thing, what's left will be the region that you want. So I'm not going to do that right now, but that's just a little homework preview. I suppose I can do one example of applying that formula. So all these cool different polar graphs we can get. How about, anyone know what r equals theta looks like? Anyone know off the top of their head what this polar graph looks like? So at 0, it's 0. At pi over 2, it's pi over 2. All right? At pi, it's pi. At 3 pi over 2, it's 3 pi over 2. At 2 pi, it's 2 pi. So let's sort of connect these guys. We would call this a spiral. So let me draw, how about 2 spirals? So that's r equals theta. R equals 2 theta would look like basically a similar spiral, but just twice as big. And if I wanted to calculate, let's say, how about this area right here, then the green area here, according to the new formula, it'll be the integral from So my angle starts at theta equals pi over 2 and ends at theta equals pi. So it'll go from pi over 2 to pi. And it'll be a 1/2. Let's see, the outer, what's the outer radial function? The 2 theta. The inner one is just theta. So that should give me the green area. You can work it out here. This is pretty easy. This is 1/2 the integral of 4 theta squared minus theta squared. So it's 1/2 the integral of 3 theta squared. So that's 3/2 times theta cubed over 3 from pi over 2 to pi, which is 1/2 pi cubed minus pi over 2 cubed, which is 1/2 pi cubed minus pi cubed over 8. That's 1/2, that's 7/8 of pi cubed, so we get 7 over 16 pi cubed. All right. Well, I thought I would end this lecture with some cooler graphs. Like I went through all this work of graphing these polar graphs and making tables, and it was kind of a lot of work, but let's sort of jump to just the cool part and have a graphing utility do the annoying work of graphing it for us, which is why I brought my laptop, and I intend to hook it up right now and and see if we can show you guys some oh, not that dark. It's still kind of dark. I don't need it this dark. Okay, let's see if I can hook this up here. Hey, oh, sick. All right. So, all right, let's try plugging in some graphs and see what they look like. Like we already did. R equals. Okay, so for example, let's look at my sine 3 theta graph. Just make sure that looks like what it's supposed to look like. Okay. So that's this one right here. Okay. Should I try, what if I made it a 4 theta? Oh. Yeah, it's kind of like, you might have thought there would have been 4 petals, but no, there's actually 8 there. Or how many petals should we have if I make it a 5? 5? Let's see, what about sine of 10 theta? Ooh, that looks, what about 100 theta? Whoa! Okay, so that's pretty cool. What if I say go back to 10, and what if I maybe do 1 plus this? Oh, no, okay. 1 minus. Let's see what other kind of cool shapes I can get. How about 1 minus, oh, that's kind of weird. Okay, let's, how about, what's another cool one? Okay, what if I did like R equals, how about 1 plus cos theta. Let's turn this one off. Times, how about theta squared? plus 2. That's kind of weird. Okay. And how about, what if I just took the sine of all this? Okay, all right, well, that's kind of sine of this. How about, okay, what about, let's try 1 plus 0.9 cos of 8 theta. And how about 1 plus 0.1 cos of 24. Okay. How about .9 plus 0.05 cos of 200 theta, 1 plus sine. What's it? So as you can see, you can get totally random shapes. Like, I don't know what this would look like in real life, you know, but yeah, you should just like try like plugging in some, I'm going to be on UCSD memes for sleep-deprived teens, aren't I? All right, yeah, so that is that, and I guess that's probably a good place to stop. I don't think I'm going to top that one, so. All right, guys, happy